All right, so last time we were playing around with this implementation of our binary search tree. Before we continue, I want to give it a little bit more of a workout. Remember that we've got our comparator here. We're just going to deal with integers. We added 10, 20, and 30, and we made sure that each one of those things was added correctly. And we also used this utility here to convert it to TXIE, which is a package in LaTeX that allows you to draw, do arbitrary drawings, but it also, in this particular case, it allows you to do tree drawings. What I want to do is, I don't want to do 10, 20, and 30. I want to do something that'll give it somewhat of a workout here, right? Let's go ahead and do it with just a bunch of random numbers, right? And say 10 random numbers. For int I equals 0, I is less than, let's say 10, I plus plus, right? Let's just go ahead and insert 10 random numbers into this tree. bst.add, and then I need r.nextInt, and we'll keep them small here at 100, means I need a random number generator. R is equal to a new random. It seeds, by default, it will seed it according to the current time. So we should get a different answer every single time that we run this, right? Let's just make sure that it doesn't crash, first of all, right? It doesn't crash. Doesn't crash, doesn't crash, right? Now let's actually make sure that this is a binary search tree in structure. Of course, I could go back to my debugger like we did last time and then exhaustively check everything. Those are 10 things though. I want to do this visually, and which is why I like doing things like this with TXIE and other graph drawing algorithms and packages like this. Let's take a look at, so 90, is everything over in the right subtree greater than it? Yep. Is everything in the left subtree less than it? Yep. Is 62, everything over here is less, 66, everything over here is greater, right? And it passes the sniff test to me, right? We're all good? Right. All right. I still want to give it more of a workout here, right? For example, what about this one? I want to know that if I put stuff into this into a tree, first of all, if I just put these numbers that are on the screen right now into a tree in a random order, am I guaranteed to get out this tree? Nope, not at all. Because what if I had inserted the 95 first? Then 95 would be the root, and everything would be in the left subtree. Right? What order could I go in to ensure that the tree gets built like this, though? What would I have to insert first? Let's just take care of that answer. Right? I'd have to insert 50 first. Okay. What would I have to insert next? Either 40 as its left child or 60 as its right child. Either or. Right? Let's go ahead and go with 40 next. Right? So 50, 40. What could I do next now? 60. Okay. So 50, 40, 60, do we start to see a pattern emerge? 20, 45, 90. Yeah, breadth first search. If I looked at this from a BFS perspective, then all I need to do is insert it in those orders. In fact, I've done this over here in the tree utils. Where is it? There it is. 50, 40, 60, dot, 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 right? This is how I actually, actually did this, right? Tree util, let's do it down here. Because I'm going to want to come back to that. BST is equal to tree utils dot large binary search tree. And let's go ahead and output that and see if that works too. Okay. So was I able to replicate my original figure here that I've been using for all of our examples, right? In fact, that's how it was generated to begin with. Right. There it is. And does it match? Looks like it to me. Right. Okay. All right. Excellent. I don't have my iPad with me today, so instead I've got this tree visualizer. It's not the best one, but it's the only one I could find that was just a straight up BST instead of a balanced binary search tree. Right. There's that 10, 20, and 30 that we did last time, and we can go ahead and play around with this. For example, if you wanted to search for 48, right? You can visualize, or let's search for 48, excuse me, 48, right? You would end up traversing right, or left, right, right, left, and then find it down there at the bottom. If you wanted to search for something that doesn't exist, say 14, right? Left, 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 right, left, right, right, and then you'd find that it's not there. Okay. I'm not really giving the find all that much of a workout here, but that's okay because I have a high assurance that it actually works. Okay. Now, before we go on to do the last operation here, let's look at some ways that we can improve this. First of all, keeping track of the size. I like that. Let's go ahead and make a private int size. How should we initialize that in the constructor? How many things have you put in so far? 0, right? Every time you add something, what do you need to do to your counter there, to your size? ++. All right. Down here, where would it have been? It's already in the tree, no operation. Do we hit ++ then? Nope. So otherwise, we insert it down here. This dot size ++. Okay. We haven't talked about delete yet, but eventually we're going to want to go -- if we delete something. Right. Obviously, searching for something does not result in a size increase or decrease, so that we're all good on that front. All right. Is there another way that we could improve this class? Well, first of all, I'm going to have to-do documentation, right? Okay. But also, let's go ahead and improve this method here, the add method, right? Adds the given value x code to this BST, binary search tree, if it does not if it is not already contained in it, it does not already have it, right? Plain English there. Right? If the element already exists, this it has no effect. This method has no effect. Right? No operation, right? Remember, if we already find it, it's already in the tree, it's no operation, we immediately return. Okay? Is there a way that we can improve this to be more useful, though? Right? Yeah.
You could like return true or false if it changes the code.
Yeah. We did that before already with linked list, or we did it somewhere, I think. An array list. I forget what we did it with, but if it has no effect, then we can communicate that effect, right? And if it is already and returns code true, that the insertion had an effect on the binary search tree. If the element already exists, this method has no effect. This method has no effect and returns false because it had no effect. Okay? That means here, if we're creating a new root, it has an effect, so return true. Right? Here, it's already in the tree. We had no effect, so return false. And here, we had an effect, so return true. Oops. True. There we go. All right. I like that even better. Another improvement. We're probably going to be searching for something a lot, right? In fact, that's what we did up here. We searched for where it should be, right? And if it was already there, we returned false. Okay? Is there a way that we could take this and make it into more of a convenience method? Right? For example, what if I were to take this and have a public tree node T, or of elements of type T, get node, right, there we go, of containing that element. Okay? And I were to copy paste that code here. Now, if we find what we're looking for, we're not going to return the element. Instead, we're going to return that tree node. Right? Return current. Otherwise, we'll return null down here because we didn't find it. All right? I like that because now we don't have to repeat this code here. Right? We can just say this dot get node or get node, right, of elements of type X, right, and return it. But this is a little bit more useful because now we can reuse this. Possibly we could reuse it up here where we're trying to find a tree node with that particular element in there. Right? All right, and it changes this into a one-liner. Right? Okay? Dot get element. There we go. Oops. That's susceptible to null pointer exception, isn't it? What if it doesn't exist? Then let's go ahead and say tree node t node is equal to, oops, not that, this dot get tree node. And then if it's not, if node is not equal to null, then we can return node dot get element, else return node. Right? And I don't do it often in class. Oh, sorry, what? No, sorry. There we go. I don't do it often in class, but I generally don't write stuff like this in practice when I write stuff. I'm doing it for demonstration purposes, that if it's not equal to null, then you can go ahead and execute this and return that value. Otherwise, you return null. When you get used to programming, you like this shortcuts. And one of those shortcuts is the ternary shortcut, right? Return what? Node equals, not equals null. Yeah, we'll go ahead and keep the same pattern. Null, question mark. If it's not equal to null, return that. Otherwise, return null. Right? That's generally how I would do it in practice, right? Because it's shorter. And once you get used to the ternary operator here, right? That all it's doing is it's an if-else-if statement. If this is true, question mark, then it takes on this value right here. Otherwise, else, it takes on this value right here. And that's what I would generally do. Okay. Another improvement here, right? Here I've got a to-do documentation. Right? And the other improvement I want to make is with this one. Right? So, retrieves the tree node containing the given element x. If it exists, returns null. Otherwise. Okay. Should that be public? Get the node containing x. Here's your tree node. Yeah, we called those things what? It leaks out information. It leaks the abstraction out. I definitely want to use it because I want to use it down here and might want to use it somewhere else, right? But I don't want to leak out that information to the outside world. You're allowed to call search, right? If I give you x, then you return x. Right? Actually, more documentation on that. Let's talk about that in a second. But otherwise, I don't want to leak out information to the outside world there. That there are a bunch of these tree nodes, and then you can start going mucking with them and changing the left child and changing the parent and screwing around with my tree. I don't want you to do that. The tree screws around with itself, right? But you shouldn't be allowed the inner workings of the tree, right? We mentioned it yesterday, but briefly, that we're just going to use integers all over the place. But let's review what happens when you, does this really make sense, right? So let's go ahead and write the documentation for this. Retrieves the given, retrieves the object or the value that matches the given dummy key code x. Right. In fact, you might even want to call it key instead. Right. So it doesn't make sense on face at first when you say, "Oh, here's x. Can you find it for me?" Right. And then you find x and then you give it back to me. I had it the entire time, didn't I? So why am I even asking for it? Right. This goes back to CS1 and back to the beginning of the semester. You're not actually giving you x. You're giving you a dummy key. Remember when we searched for a bunch of books for a particular book by a particular author? Well, we had an author and we had a book, but we couldn't search based on that because they're not comparable. A book and an author are not the same type of object. If you want to search a collection of books, you need a book as a key. So we created what's called a dummy key. We created a book with that author in it. What about the title? What about the ISBN? What about the release date? All of those were left to be null because this comparator over here looks at these books, looks at this book, and only compares the authors. That's why it's a dummy key, right? This X here is a dummy key, right? Okay. All right, that looks good. Are there any other improvements? Maybe some convenience methods. Let's see. Contains, right? Public public Boolean contains tx, right? You might just want a yes or no answer to your question, right? And in which case I can say or return this dot search for x, and that'll either return null, in which case you didn't find it, right? Or it'll return something that's not null, in which case you did find it. So just say search for it, and if it's not null, then yeah, it contains that element x. Now that we've got a size method, public int size, return this dot size, right? That seems reasonable too, right? I don't know what else. Can we simplify this method? Oh, here's a good question. Can we simplify this method here by now using our getNode method over here? Remember, we were keeping track of a current and a previous. If I just use this method blindly over here, and I get the node to insert something, right? We're adding something here, right? I'm not going to have previous anymore. So there's an instance in which I'd say, well, no, it's better to repeat the code now because you are doing something significantly different. You're keeping track of two nodes. What you could do is you could change this so that it returns a pair, the parent, the previous, and the current, right? And I think we've done pairs before, but yeah.
I don't remember about the tree node thing, but could you get the parent from a node?
You can, I believe so. Let's go ahead and take a look at the tree node class. And yes, you can get the parent, but remember, you've already fallen off the edge of the tree, so you can't get back to the parent because this is null, right? So again, this, you could maybe come up with an idea for simplifying this, like say, get parent and child, right? Instead of get parent and child and current, yeah, something like that. And I'll return two tree nodes. Of course, you can't return two objects in any programming language. Instead, you'd have to tuple it up and return a pair, right? But that's going a little bit too far, and that's a Yagni at this point, right? If I ever really want to do that, then we'll go ahead and do that, right? All right, that's good. And we can make this to do, restore this to private. The only reason that I'm making this public right here, this tree, this root, is because I want to be able to do stuff over here in my tree utils, right, with Tixie and stuff. Okay. Otherwise, where would that Tixie properly belong? It operates on data in a tree, right? It does tree things. Where does it belong? In the tree utils class? No, in the tree class, right? Okay. But I didn't want to put that in right away, so I'm not going to do that. Right? All right, fine. Let's go ahead and take care of the last part of CRUD, the D, the delete. Okay. Let's come over to this tree. Let's delete 48. What is the process there going to be? Right there, there's 48. It does exist. Actually, let's ask another question here. 14. 14 does not exist. What should happen? It's going to search for it to see that if it can find it first, right? It finds that it doesn't exist, and so nothing, right? No operation. All right, fine. Let's go ahead and delete 13 now. Right. The first thing you need to do is find it, and it will find it. 13. What would be involved in deleting 13? Well, it has no children, right? So it just gets deleted. Its parent is set to null if you want to do that. Otherwise, you could just say its parent's right child equal to null in order to get rid of it, right? So how does deleting work? Well, that's the first step, right? First step is to find the node that you're looking for, right? All right, so here's case one. Case one. The node is a leaf, right? If it's a leaf, then no problems with deleting it, right? Make its parent point to null, right? And you've ended up severing it, right? Point to null. However, careful, is the node a left or right child? Question mark, right? And so you need to be able to, if you go up to the parent, you you need to be able to delete the left or the right depending on what I am, right? In this case, it was what, 13? So 13 was a right child. So we jump up to the parent and say, all right, delete your right child. Your right child is now equal to null. But if you were to delete, say, 2, right, then once we find it, we say, oh, no, that's a left child. So go back to the parent and set the left child to equal to null in order to delete it. All right. So step 1, find it. Find it. Hey, guess what? We have that nice convenience method, right? So this dot get node of x. There's my tree node. Tree node to delete. T to delete is equal to that, right? Step 2, make sure that it actually exists. If to delete is null, what did we say? That was a no operation. Just return null. Remember, I'm returning the element that I'm deleting, right? So let's put that in our documentation. Removes the given element from the from this binary search tree, returning it if it existed. Right there. Do I need to decrement my size in that case? Nope, because you didn't do. It was no operation, right? Otherwise, let's do part 2. Delete it. Case 1, right? It has no children. The node has no children. Right? So how do I determine if the node has no children? To delete dot has left child, has right child, right? Dot has left child, or it doesn't have the left child, and to delete dot has right child not. Right, there we go. I don't like that logic. Right? In fact, this sounds like a node thing. Right? Do you have any children? Yeah, you have a left child, you have a right child, right? But do you have any children? Where should we be putting that? Probably over here in the node class, right? Is root is leaf? Oh, remember that we already did this. Num children, right? I thought this would come into handy if to delete dot get num children is equal to 0. Sorry, what? Oh, is leaf. Thank you. That's even better. Right? Dot is leaf. Right? It has no children, i.e., it is a leaf. There we go. That's even better. Because if it's a leaf, then that's shorter code, right? I don't have to say that it's equal to 0, right? So it has no children. We just need to delete it. All right. How did we do that with, say, 12? Right? We need to determine, am I a left child? Or if it was 95, am I a right child? Right? So, case 1a, if the node is a left child, then parent dot set left child equal to null, right? Otherwise, case 1b, if the node is a right child, then parent dot set right child to null, right? And in either case, you're going to decrement it, right? We'll take care of that later, though, right? How do I determine if the node is a left child? That'd be a great question to ask the node. Is left child? It doesn't exist. But if it had existed, that would have been easy, right? Well, let's make it exist then. Right? Let's go back to our tree node class here. And I'm not going to say get the left child or you have a left child. Am I a left child? Public Boolean is left child. Let's put the logic to that in here. Right? Now that means that I'm going to have to go to my parent and ask, am I, so there's this nice, what? All right, there's this nice riddle. So a guy walks up to a painting, a portrait, and says, I know this man, right? And he says, in a riddle, he says, Brothers or sisters I have none, but this man's father is my father's son. Who is in the painting? Him, right? Brothers and sisters I have none, right? I'm an only child. But this man's father is my father's son. Who am I? Right? It's just a self-reference. This man's father is my father's son. So, how do I determine if I'm a left child or not? I ask my parent. This dot get parent, right? Dot get left child. Left child. Right? Is that equal to me? And how do I say me in Java? This, right? So, if this parent dot get is equal to this, then return true. Right? Otherwise, return false. Right? Now, of course, I'm going to simplify this in a second here, just by returning this statement here, right? But be careful. When is this not going to be allowed to get your parent? If I'm not a root, right? If I'm a root, am I a left child? If I'm a root, am I a right child? No. So if this dot is root, right, return false. Right? There we go. So I'm taking care of that one corner case. If I'm a root, I'm not a left child, I'm not a right child, I'm no child. Right? All right? Now this is safe. And it's safe to simplify that. Right? So if it's a root, false. Otherwise, as my parents, left child equal to me, then I'm a left child. We're probably also going to want the right child, right? Right? Is right child? And is right child, or get right child? Right? Same logic there. Right child, there we go. Right? That makes it so much easy over here, right? If you are a left child, then to delete dot get parent dot set left child to null. There. Right? And then I can also ask the other question, else, right? And I won't ask the question because it's either the left child or the right child, and that's it, right? If the node is a right child, then we say to delete set the right child. There we go. Okay. All right. There is our first case, all done. Let's test it first. Right? And by the way, what should I do at the end? This dot size minus minus. Right? I'm not obviously not going to change it up here, but I will return. Oh, I need to return something too, don't I? Right? What do I need to return? To delete dot get element. Okay. All right. Let's test it over here. Tree node. Now we might come back to that, but let's go ahead and get rid of that. Get rid of that, and let's go into our demo class over here. Remember, it's the large binary search tree. This guy right here. All right. Let's go ahead and test. Should I test deleting 50? I haven't done that case yet. Right. Let's test deleting 12 and maybe 95 because one of those is a left child, one of those is a right child, right? So let's go ahead and bst.delete 12, bst.delete. What was I say? 95. All right. All right, and then we'll print it out and see if we get what we're looking for here. There you go. Copy that, and let's come over to my overleaf and see if those two actually got deleted. Recompile it, and 12 and 95 are now gone. Right? Everything else is still intact. Right? Good. Right. All right, well now, what about 49? 49 is not a leaf. Right? So what could we do in that case? What's that going to look like? Let's come over to the visualization. What about 49? I'm about to delete it. Right? So first of all, I need to find it. We've already done that part. But then I need to delete it. So do you want to lose 48 here? No. So what could you do? Take that 48 and promote it back up. It only had one child. And if you have one child, you've got node to node to node. That's nothing more than a linked list, right? And a linked list, all we did to delete something was make the previous point to that one, make that one point back to that one if it's a doubly linked list, and the thing in the middle is now cut out, right? So, case 2. Case 2. The node is has one child, right? In this, we can promote the child up, since there's only one child, and I'll put that into quotes there. Promote the child up. Right? In other words, it is no different than deleting in a linked list. Okay. All right, come back over here, and let's do case 2 now. Case 2. Else if to delete dot get number children dot num children is equal to 1. Right. There's not really a term for that we could put into that class and say it has only one child. I mean that's kind of overkill at that point, right? So I'm just going to say that it has one child, right? Promote the child up. Dot dot dot. Actually, let's do case 2 here. Case 2, only one child. So promote the child up. However, there are going to be 2 subcases here. Case, or 2A, case 2A, right? If the only child is a left child, promote the left. Case 2B, if the only child is a right child, promote the right. Okay? So I need to get the child and determine if that's a left child or a right child. So let's go ahead and get that child. Remember that I know that it's 1 here. So to delete dot has left child. There we go. If to delete has a left child, then you know that it's a left child. Else, and then you have case 2B right here. Let's move that up over there. And let's move this in over here. There we go. So if it only has a left child, promote the left. Otherwise, you know that it only has one child, otherwise you wouldn't be here. All right? All right, how do we promote the left child? To delete dot get parent dot set left child to deletes dot left child. Yeah, what's wrong there?
It might not be a left child.
Yeah, not only do I, so to delete has a left child, I also need to know with respect to my parent. Am I the left child of my parent or am I the right child of my parent? Because that's the one that I need to set. No, not parent. To delete, get their parent. Yeah, I'm going to have a bunch of, another case here, right? So, case 2A I, and then case 2I AI. How do you want to call these things? Case 2AI. There you go. All right. There. All right. So, let's map this out. If to delete dot get parent to delete if I'm a left child is left child. All right. I am a left child, so I need to set my parents left child to my left child because I have a left child. I being to delete. All right, there we go. Else, case 2AI, and I'll come back and fill those in later, but to delete dot get parent dot set right child to delete dot get left child. There we go. All right. Now we've got to make sure that if we cut and paste this for this case down here that we fix everything. But let's just make sure that that we understand what's going on here. So that to delete is a left child. So set parents left child to my left child. And likewise, to delete is a right child, so set parents left child to, or parents right child, excuse me. Right? What am I forgetting in all of this, by the way? What about the child? Right? I need to set its parent as well, right? So I can do that in either case. That doesn't depend on whether or not I'm a left child or right child. Instead, to delete dot get left child dot set parent to delete dot get parent. There we go. All right. Should I'm hesitant to even copy paste that. Let's just go from scratch. To delete dot is a right child. Right? Oh, I guess no. I'm already there. Right? That's my else statement. Right? I am a right child, so if to delete is a left child, right?
Yeah.
Then to delete dot get parent dot set left child to delete dot get right child. There we go. Good. All right. And then else to delete dot get parent dot set right child to delete dot get right child. And then this, but with a right child instead. Right child. There. Now, I'm sure that you can collapse that down and be clever about it and realize that, well, okay, I can go ahead and just, set one of those nodes and maybe there's some way to collapse this down, but otherwise, that's good enough, right? Let's test it though, of course, right? Now remember that we've already deleted 12, and actually let's go ahead and get rid of those. No, let's keep those in, right? And now let's go ahead and delete something like delete 49 and then 60. Right? Why 49? Because it is a right child. By all rights, code coverage, I should have 4 cases, right? Where the node you're trying to delete is a left child or a right child. Where the node that you are trying to delete has a left child or a right child, so 2 times 2 cases. So 60 would be right with a right. 49 would be a right with a left. That'll be at least 2 of them, 49 and 60. All right. 49 and 60. There we go. And run that. And visualize it. Come on, where are you? All right. So 49 should be 48, and then 90 should be promoted up now. 90 should be promoted up, right? I didn't screw anything else up, right? 80, 75, 85. Great. All right. At that point, what else can we test? Because we had a right child. Both of them were right child. I don't know. We could start deleting everything if we want to. 24 and then 45 and whatever else, right? But I'm convinced that by all rights you should have to do all 4 cases there, because if I were to put this into JUnit and I were to run that code coverage test, at least one of these cases, say that one, would not show up as being covered. Okay, because I need at least 4 cases there, because now I'm 1, 2, 3 levels deep there. All right, else. Case 3. What happens with case 3? Let's try to delete, say, 50. Yeah. What happens if we try to delete 50 here? Yeah. Does 90 get promoted? Or does 40 get promoted? Well, can you promote 90? Then 90 would end up having a left child of 40 and 80. Can you have 2 left children? No. Besides, what if 90 had, like, let's insert 100 over here, right? Now 90 has 2 children. Can it be promoted up? Can you have 3 children? No. All right. What if I just blanked that out? In other words, I made it look like this. There's 50. Blanked it out. And I saved it off so that we can eventually delete it. Right? What could I put in its place to preserve the binary search tree property? Remember, whatever I put up here, everything over here has to be less than it. Everything over here has to be greater than it. Okay, so you could put up 90, right? But let's think about the right side first, and then we'll think of, because I read left to right. So let's think about the left side first. What in the left side could I promote up here so that everything is less than it? The greatest, right? 48. Right? So can we put 48 up there now? Come on. I thought I was typing. 48. There we go. All right. But now what about 48? We need to take care of that. Yeah, remove it. Is there a problem with removing 48 here? At least in this instance? No, because we already know how to do that, case 1. Right? What if 48 had a left child? Then that's case 2. Right? What if it had both left and right children? Then it wouldn't be the greatest, exactly. Right? Because a right child is going to be greater than 48, in which case you would have promoted that instead. Right? So that's the idea. Case 3 has 2 children. Case 3, both children are present. Right? What you need to do is go to the left subtree and find the maximum value. Then promote it and delete it, that node. Right? Alternatively, what could you have done? Go to the right subtree and find the, not the maximum, but the minimum value. Promote it. Promote it and delete that node. Right. Okay. So let's get some infrastructure here basically first. I'm going to go to the left subtree and I want to find the maximum. Hey, that sounds like it might be a really, really useful thing, right? Maybe we should put that into another function. Public t get max. And if you want to go the other way, you could also get min. Public t get min. Right? But I don't want to just get the overall max or the overall min. I want to go to the left subtree and then get the maximum with respect to that. So let's put in another version here of get min and get max that takes a tree node, and you can start at any arbitrary location. Node. There we go. You can start at any arbitrary location and get the maximum or minimum at that node. Right? Okay. How does that help me with these first 2 methods? If you want the overall max value, you would start where? At the root. This dot root dot get dot. That returns. I guess we want to return a tree node here too. Yeah, let's return the tree node instead. Right. So dot get element. There we go. And return. Sorry. And if you wanted to do the minimum, then start at the root and get the minimum. There, just one-liners. In fact, that's a pattern that you should see all over the place, that you have this one generic general function, and then all these other functions, these convenience methods, they just call that with different inputs, right? Or some combination of other things. Should this be public? Should you be allowed to get the tree node and give me a tree node? No. Private and private, right? Okay. How do we get the max starting at a particular node? Let's go back over here. How do you get the max here? Starting at the root. Keep going right. Keep going right. Keep going right until you can go no further. Right? So let me codify that. While, in fact, I'll do another node here. Tree node t current is equal to node. We'll start at the node, and while current dot has right child, go to it, right? Current is equal to current dot get right child, right? I'm looking ahead here because I don't want to fall off and then have to keep track of a previous and a current, right? Just keep going right until you can go right no further. Then return current. What would that look like for min? Start at whatever node you gave me. While you have a left child, get the left child until you can go no further. Right? There. That's really nice because now down here with that infrastructure, we can find the minimum of the left child, right? So tree node t min node is equal to, or I guess we want the max node if we're going left. Max node is equal to to delete dot get left child, or sorry, left child. And we'll pass that on to max. This dot get max of that. Right. So there's the maximum node that we need to promote up. Okay. So how do we do this? We've already found the maximum node. To delete dot set element to max nodes dot get element. That'd be the most convenient thing. And now maybe you have an argument for making this a little bit less than immutable, right? So now you can say get, where's the get element? I want it right next to each other. Get element, public, void, set element, t element. This dot element is equal to element, right? It's just, now I have a reason to, right? Remember that generally you want to prefer things that are private and prefer things that are immutable unless you have a very good reason to do so. Capital V, capital G, capital R, right? And I think that this is a very good reason to do so because I don't want to have to shuffle around the parent and the left child and the right child and end up with a big giant if else, if else, if else, if, like I would up here, right? I'm just going to promote that. Now what do I need to do? I need to remove the max node, right? Guess what? We have a function to do that, right? Max node dot get element. Careful. All right. Yeah, there's two now, just like over here in my picture. There are two 48s. It's going to end up deleting this one and getting me into a big, giant, non-stopping recursion, right? Okay. If I'd done that then. So max node, get it. I've got my max node. That's not going anywhere. Go ahead and delete the max node. Now that's out of the tree, but I still have my max node over here, and I still have its value. In fact, what I could do is I could save off that value. To replace is equal to max node dot get element. If I really wanted to be safe here, I could, of course, go ahead and set that to the element to replace. There. Yep, there we go. Is that right? Delete the thing with the max node. I think that that's right. All right. How can we be assured? Let's go ahead and now delete 50. Just as one chest, and then we'll come back next time and see if we're right by deleting everything, right? All right, run that. It works, or it runs, I should say. We're about to delete. Oh, darn it. Okay, so this is an intermediate. So does 48 end up being up there, and then does this 48 end up disappearing? Hey, it did. Yay. Really want to give this a workout because we've got one more minute here. Let's go ahead and just go ahead and do that. What should it look like now if I delete 48? 45 should come up and 45 should go away. Hey, cool, right? Think of a corner case really quick that we're going to do on Monday. We never allowed that to get in, so that should be okay. Delete, 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 and you're only left with one thing to delete. Right? What happens then? Yeah, we're going to end up setting the root to null. Right? Well, maybe that's a clear method that we do. Right? So keep that in mind for Monday, and that's where we'll pick it up. Otherwise, have a good weekend.